Hello everyone, welcome to Statistical Methods. In this video I'll be explaining the quadratic approximation of the log likelihood function and also the asymptotic normality of maximum likelihood estimates. If you'd like to study this in detail, then look into the chapter 4 of the lecture notes, in particular the first sections until observed or expected Fisher information to estimate variance of the MLE. Okay, let's get started. So before we actually look into the quadratic approximation, we need to introduce a new distribution. And it's not that new because you know the univariate version. So we need to consider or need to learn about the multivariate normal distribution. So let's start with the univariate normal. So the univariate normal is an old friend of yours. So we have a random variable distributed, or it's normal with a mean and a variance. Then we know that the density is density function depends on two parameters, namely mu and sigma squared, and that's 1 over the square root of 2 pi sigma squared, and then e to the power of minus 1/2 x minus mu squared divided by sigma squared. So you should be familiar with this. And in particularly, let's remind the meaning of mu and sigma. So the mu is of course the expectation of x, and sigma squared is the variance of x, and this is defined as is also an expectation. It's the expectation of the squared difference of x from the mean. So that's the variance, and you can also write it as follows, namely it is the expectation of x squared minus the expectation of x squared. So that's the univariate normal, and we've seen examples already that we're interested often in not just one parameter but several parameters, and we put them together in vectors, and we would like to quantify the uncertainty of these vectors, so we need vector valued random variables. So instead now we look into x is a vector, and this has components x1, x2, xd transpose, so you can also write it like this, x1, xd. So that's your vector, and each component is a random variable, and the whole thing is a random vector. And in a subsequent course, namely in multivariate statistics, we'll work a lot with random vectors. In this course we only very rarely work with it, but if we do, we need a very specific distribution, namely the multivariate normal distribution. So we can generalize the above distribution to the multivariate normal that is usually written like this, nd for dimension, and of course the univariate normal has d equals 1, so if d equals 1 we get univariate normal. So this has two parameters, namely the mean vector and something called the covariance matrix. So the covariance matrix is what I'd like to discuss now, because the mean is trivial. So the mean of this x is just this, and it's just the expectation of each individual component. So it's mu1, mu2, and so on. So that's trivial. But what about the variance? So the variance of this thing here is actually defined very similar as above, or in fact it's more or less identically defined. So the variance of x, here we had the expectation of the squared deviation from the mean, and that's exactly what it's how it's defined here as well, only that we can't take the square root because it's a vector. So we have the expectation of x minus mu, so mu is the mean vector, times x minus mu. These are two vectors, so we have to transpose one and we transpose the second one, and that's a matrix. So that's a d times 1 vector, that's a d times 1 times d vector. So let me correct this. So 1 times d vector. So, and you can also write this similarly as above, as the expectation of x transpose minus mu transpose. So this is the definition, and this is called the covariance matrix. So covariance matrix. So we will use this later as well, but for now it's sufficient to memorize that this is a generalization of the variance. So it's a symmetric matrix. So sigma is symmetric. So, and you can write it down like this. So on the diagonal you have the individual variances of the x1, x2, and so on, and then here on the off diagonal elements you have the covariances, the proper covariances. So as I said, the key thing is this is when you, so in more than one dimension, the variance is not just a single number, but it's a matrix. So for d larger 1, variance becomes a matrix, so it's not just a single number. And this matrix is sigma, and it's called the covariance matrix. So now we can come back to the multivariate normal. So we have x is distributed as multivariate normal with a mean vector and with a covariance vector, so a matrix, I mean. And the distribution, that's the distribution, and the density, the corresponding density of the multivariate normal is 2 pi, so it's fx, independence of x is a vector, everything is a vector, mu, and this is a matrix, equals 2 pi to the power of d divided by 2, then the determinant of sigma to the power of -1/2, and then the e thing that we had before, only that it's -1/2 x minus mu transpose sigma inverse x minus mu. So that's the, let's do it, make it a little bit smaller. Can we do this? Let me see. Ah, yeah, okay. So it's now a bit smaller. So this is the density of the multivariate normal, and for d equals 1, we get exactly the univariate normal density. So it is a proper generalization. And it also looks like the normal distribution, only that it's more multidimensional. So in 2 dimensions you can actually like visualize it, because it looks like a bell curve. And in the 2 dimension, of course, it looks like a real bell. So it's an object. And this, the key thing is that this multivariate normal distribution will now be used to approximate the distribution of the maximum likelihood estimates. So one last thing with regard to the covariance matrix. So the covariance matrix is, if you recall again, so sigma is variance of x and is a matrix, and you can actually decompose this, so it has entries sigma ij, and the sigma ii is actually the same as as the variance with only one index. So you often see these two things. This is a little bit confusing. So if there are 2 indices, it's really an entrance of this matrix, and the diagonal entries, like the ii entries, are actually corresponding to the variances, and the variance, of course, you write with a square. So, and we can define now something that's called a correlation. So a correlation is a standardized covariance so, and it's defined as follows. So you take rho is our rho ij is the correlation between xi and xj, and that's defined as the covariance between I and j divided by the product of the variance of xi and the variance of xj, and then you take the square root. And you can easily see that rho ii is 1, because then this becomes 1. So when we create a matrix consisting of these entrances of the correlations, so that's a rho, capital Rho, it's not a p, then we have a matrix that has 1 on the diagonal, and then we have rho ij, rho ji on the off diagonal. So this is symmetric as well, of course. So rho ij is the same as rho ji. So correlation is a standardized covariance, and this is a measure that allows us to measure the linear dependence between variables. Okay, so that's it with what we need in terms of multivariate statistics. So if you're interested more in multivariate statistics, then I recommend that you consider taking part in the multivariate module that is offered in year 3. More multivariate statistics. In year 3. So, but this is all we need for our likelihood analysis. So now we are continuing. So talking about likelihood, we know that MLE of mu and sigma squared for univariate normal. So we know this because we know that mu hat is 1 over n x k, and k goes from 1 to n, so that was the mean, so it's x bar. And we also know that the maximum likelihood estimate of the variance was also from 1 to n is xk minus x bar squared. So that's s squared, and we can do the same thing, so we derived this using the normal distribution. We derived this ourselves, so see derivation, see earlier derivation. So we can do the same thing now for the multivariate normal for n d mu sigma, and we can write mu vector hat is 1 over n, and then the sum over all the vector observations. So we take the mean, and exactly the same we do for the estimated covariance matrix. So that is also 1 over n, and then we take the sum over k equals 1 to n, and then it's only now it's vector, so xk minus mu hat vector times xk minus mu vector hat transpose. So that's exactly the same. So that's also the MLE, and you can, if you like, you can try to solve this yourself, but this requires, at least for the covariance matrix, it's actually not so trivial. So it's not done in this course, but we'll do this in the multivariate statistics course. But we'll do in the worksheet, we'll solve this numerically. So this is the analytic formula, and in the worksheet we'll try to do this numerically. In worksheet I'll show you how to optimize the mean numerically. So find new hat ML numerically by numerically computing the likelihood function and then maximizing. So these are maximum likelihood estimates, but you can also derive it analytically, but we'll do it numerically just for doing something different. In the in the lecture notes you'll find a little bit more info. In particular, you'll also find about other notations. Notations for the MLE. So what I gave you is the notation where you use the data vectors, and then there are two other notations. One is a component notation and one is a matrix notation, and both of them are given in the script for completeness, but I'll mostly use this notation. So I use data vectors, and this is I think it's the shortest notation and also the one that is closest to the univariate notation. Okay, so that's it for the multivariate normal. Now let's go straight into the quadratic approximation of the maximum likelihood function. So that's the main topic, and the reason why we're talking about the multivariate normal, because you will see that it will appear magically. So quadratic approximation of the log likelihood function. So what does this mean? So the purpose is, so let's say we have a general likelihood function and we have our parameter theta, then we have our log likelihood function here, and then we have somewhere a curve like this, and of course here we have our theta hat ML. This is our maximum likelihood. And by doing a quadratic approximation, what we do is basically we fit a parabola here, and so the maximum of course has gradient 0 around the maximum, and then we get the curvature, so we get the point of the maximum and we get the curvature. So how do we do this? So let's recall Taylor series. So we have a multivariate function, several arguments, and that is developed fx naught plus the gradient fx naught x minus. So we've seen this before when we did the expected Fisher information. So this is the linear term, and then we also have a quadratic term. Where we have the Hessian matrix. So we have Hessian, a term with the gradient, a term with the Hessian. And the key thing is that we evaluate the function only at x naught. So this is f is evaluated only at x naught, and we compute the gradient f there and the Hessian. So for the log likelihood, now we apply this to the log likelihood. Apply to the log likelihood function, which is a function of theta. Theta is a vector typically. So this becomes, so we apply this with x equals theta, and x naught is theta hat ml. So we develop the quadratic approximation around the maximum, and this turns out to be as follows. Namely, it's quite simple. So we get the log likelihood of theta is the log likelihood at the maximum likelihood, and now minus and I'll show you in a minute where the minus comes from, because here we have a plus, minus 1/2, and then theta hat ml minus theta. Then so this is exactly what is done here. So instead of the Hessian, we take the negative Hessian, and that's something we already encountered, namely that's the observed Fisher information. And so we have Jn theta hat at the observed Fisher information at observed Fisher info at ml, and this is the second term here, so times theta ml minus theta. So that's what you note here. So there's no linear term. No linear term, because gradient vanishes at the MLE, of course, so it's by definition. So, and now the interesting thing is, so what you see here, so if you compare this to the multivariate normal, it looks pretty much like the multivariate normal of the log density. So the log density of the log density of the multivariate normal has exactly the same thing, only that we have here sigma, so we have the inverse covariance matrix here. And if you have followed the last video where I talked about the observed Fisher information, we hypothesized that the inverse of the covariance matrix is kind of, or the variance is actually related to the Fisher matrix, and that's actually clearly indicated here as well. So this means that the quadratic approximation of any log likelihood function takes on the form of a log density of the multivariate normal. So this leads directly to the following theorem. This theorem is about the MLE. So, theorem about the MLE theta hat, and it goes as follows, namely the maximum likelihood estimator is asymptotically distributed as a multivariate normal around the true mean with the covariance matrix taking on the form of the observed Fisher information inverted. So let me write it down. So that's the theorem. So basically it says for large sample size n, the maximum likelihood estimate is normally distributed. So that's the first thing. So it's normal. Asymptotically, maximum likelihood estimators follow a normal distribution. So it's normally distributed around the mean, or not the with the mean corresponding to the true value around the true value of the parameter, and with variance following the inverse observed information. So how do you prove this? So basically you take the quadratic approximation that we did before, and then you apply some asymptotic arguments. So I'm not, in this course we won't work out the mathematical details because this requires regularity conditions. So the proof will be done in year 3 in the statistical inference course, but for now we can basically just say under regularity conditions and the regularity conditions are of course large N and the curvature, so gradient Hessian can be computed, and also what's also important, the true parameter is not on a boundary. True theta does not lie on a boundary. So basically, if you can compute the Fisher information, then you can assume that for large n, the estimate is normal distributed. So for if you have only one parameter, for d equal to 1, then we can write theta hat is asymptotically distributed as a univariate normal with the variance being the inverse of the observed Fisher information. So why is this fantastic? So this is great news because, I mean, it's really great news because this makes maximum likelihood estimation fully automatic in the following sense. So ML gives us a point estimate theta hat ML, and the curvature at the MLE gives the asymptotic variance. So we know roughly, we get an estimate of the variance of the maximum likelihood estimator, and we get an asymptotic distribution, namely the normal distribution. So asymptotic normality. So this is really good. So ML, to summarize, ML can do much more than just estimating theta. It can also assign an error to theta. Assigns error and also allows to find an approximate distribution. So that's it for today. So I hope you could, so from this session we discussed multivariate normal, we discussed the quadratic approximation, and in the end this led us to understand that the quadratic approximation looks like the normal distribution, and in the end for large n everything will look like a normal distribution. So the quadratic approximation will become better and better the larger n is, and in the end this is another cornerstone of the success of maximum likelihood. So that's it for today, and I see you in the next video. Bye bye.